General relativity predicts how light bends and planets orbit with extraordinary precision. But what if tiny deviations from Einstein's equations could explain subtle discrepancies we observe in the cosmos? The authors of this paper investigate exactly that question using DST black holes. DST black holes emerge from modifying Einstein's equations with additional terms built from the Weyl tensor. These modifications are subtle, but they produce measurable changes in how particles and light move through curved spacetime, opening new possibilities for orbital dynamics that don't exist in standard general relativity. So how exactly do particles behave differently near these exotic objects? The researchers derived new equations for geodesics around DST black holes, finding that adjusting just one parameter can reconcile theoretical predictions with observed discrepancies in both light bending and Mercury's perihelion precession. These aren't random fixes. They emerge naturally from the modified spacetime geometry. Beyond orbital mechanics, the authors investigated whether DST black holes can accelerate particles to extreme energies through collisions. They found that when spinning particles collide near specific radii, where trajectories transition from normal matter-like motion to exotic space-like paths, the center of mass energy diverges dramatically, turning the black hole into a natural cosmic accelerator. This work transforms minor inconsistencies between theory and observation into potential signatures of new physics. By showing that DST black holes produce measurable deviations in well-studied phenomena, the authors offer astronomers concrete predictions to test whether our understanding of gravity needs refinement at the most extreme scales. When black holes become laboratories for testing the limits of Einstein's greatest theory, even the smallest deviations carry cosmic significance. Visit emergentmind.com to explore more cutting-edge research and create your own presentation videos.